All right, so here we go. Um, the total magnitude on this little charge down here is in a positive y. So this is just adding up the vectors. Okay, so what we'll do, because we could figure out, we're looking at determine the magnitude of Q2. Okay. All right, so this is a 30 Newton force that's being caused by the force on Q1, caused by Q1 on Q, and the force on Q2 caused by Q. Okay. And it's a total of 30 newtons. So it's just a matter of adding up vectors. All right. So let's take a look at that. Let me draw what we have real quick. Q2, Q1, and Q1, they at least tell me how far Q2 is. It's 0.35 meters. Okay. And Q right here is at 0. All right. Q2 is unknown, but the R away is 0.35. R2 is equal to 0.35 meters. And Q1 is equal to Q is positive. Okay, and so Q1 is equal to negative 28. Negative 28 microcoulombs, and it is 0.2 meters away. So R1 is equal to 0.2 meters, and Q is equal to 8.3 microcoulombs, and its distance from each other is 0. All right, so we got it all set up. So let's take a look at this. This might be the only problem we do on this little track. All right. I know this is 0.2 and this is 0.35. All right. So I don't know what Q2 is, but I do know that the force acting on Q, is 30 newtons positive going that way. All right. So I'm just going to add up the vectors. So the force acting on because see, this is a positive charge and this is a negative charge, so they're going to be attractive. So Q is going to want to go that way. All right, so the force on Q caused by Q1 is equal to, and it's going to be in the positive y direction, is equal to K times Q1 times Q, and we'll keep it all in absolute values because we know which way it's going, divided by 0.2 squared. So I can calculate that. I can actually get that. I mean, I've got all of those numbers. I can just say what that is. All right. And so let's do it. So we'll say K 9 second e to the 9th times Q1, which is 28 second e to the negative 6, because it's microcoulombs, times 8.3 second e to the negative 6 divided by, I like to put this in parentheses too, 0.2 squared is equal to 52.29 newtons. Okay, so if the net charge is 30 newtons, then what do I know here? I know that the force on Q caused by Q2 is equal to, because the sum of the, here's the deal, the sum of the forces acting on Q are equal to the force acting on Q by Q1 plus the force acting on Q by Q2. We've already calculated the one for Q1. And we know that the sum of the forces is equal to 30 newtons. And this one is equal to 52.29 newtons plus F of Q of Q2. Well, what's Q2 going to be? Well, it's going to be negative, obviously, when we solve for it. So already I know that Q2 is since it's a repelling force, it's going to be a positive, right? Because it's going in the opposite direction. It wants to go in the opposite direction. So Q2 is going to be positive, and then you figure out what F of Q Q2 is by doing that simple algebra, and then you can figure out what positive Q2 is. All right? By doing, setting up the equation and solving for Q2. And you know the Q2 is positive because it's pushing Q this way. Q2 is pushing it that way. Because the net force, because this force is big going this way, so there's got to be a force pushing it that way. And since it's repelling it, Q2's got to be positive. Capiche? All right. Well, that was fun. I thought that was going to be a killer problem. It wasn't killer. 19. Hey, we've done this. You can do this, but this is for helium. 2 protons. So you've got to figure out what the force is of 2e instead of just 1e. And here's your radius. So you know how to do that. We've already done this one. Is this your mv squared over r? No problem there. What's 24 look like? Oh, this is fun. So let's just go ahead and do this one and wrap this lecture up. All right, an unrestrained horizontal spring has a spring constant of 35 newtons per meter. 2 small objects are attached to the spring, one at each end. The charges on the objects have equal magnitudes. Because of these charges, the spring stretches 0.029 relative to the end. Determine the possible algebraic signs. Okay, well, first of all, they either both have to be negative or they both have to be positive if they're going to stretch the spring, right? Because they got to be repelling forces. And the magnitude of the charges. What is this? Don't forget. Don't forget. We're once again, we're combining. So in this problem where you've got a spring just sitting here, all right, so I've got a spring just sitting here. Now I'm going to attach 2 charges. And when I attach the 2 charges, it stretches a certain distance x from its equilibrium point. Okay? Here's where x equals 0, and then it stretched to x, which was, what they say, 0.029 meters or something like that. So it stretched a little bit. And this was caused by the force, which is equal to k times x. They gave you k, they gave you x, so you know what the spring force is, Newton's law. Don't forget, this k is the spring constant, but the k over here, k electric, times q squared, again, because this is q and this is q, and they can either both be positive or they both have to be negative because they're repelling forces. They're doing this. Over that x squared, where k, this k, is the electric constant. Fun, fun, fun. And there you go. There's your hint on that one. These were kind of tricky, but we worked them out.